Good morning, everybody, and welcome to another live science show with Chabot Space and Science Center. My name is Haley, and today you're joining me live in my kitchen. Woo! Welcome. Today we're going to be doing an experiment that involves some stuff in our kitchen, and we're going to be talking a little bit about pressure, so it's going to be a lot of fun. But bear with me, because my camera angles are kind of weird, because, you know, you're on my kitchen countertop right now, so welcome. It's exciting. Welcome. I'm Haley. This is Chabot Space and Science Center's Life Science. And what life science is basically I'm going to walk you through a fun demonstration of one scientific phenomena. And I'm going to need your help to help me figure out exactly what is going on here. So I'm going to need you to type in the chat some of your predictions, your observations, your hypotheses, and your explanations of what you see happening here today. And together, as a scientific team, we're going to try to figure it out using one another, what we know, and then I'll explain it at the end. But in the beginning, I'm going to need your help to help me figure out what's going on. Now, during this time, Chabot Space and Science Center, like many other museums and science centers across the United States, is not open to the public. So if you would like to help support us in our mission to bring free virtual programming, such as this, into your homes every week, please click the donate button below if you're on Facebook, or you can head to our website, chabotspace.org, and you can donate there. And all of that funds pretty much all of our virtual programmings, including this, our live telescope viewings, and everything else. So if you're enjoying what you're seeing and you've tuned in many weeks, feel free to do that. We already appreciate it so much. If you can donate whatever, every dollar counts. So yeah, thank you all so much. If you already have donated, you've helped bring me live from my kitchen, so that's great. So we're gonna get going today with our demonstration, but today we're actually gonna be doing a demonstration in my kitchen that involves some heat and some materials that I wanna make sure I'm safely using. So before we get started, we're gonna do a safety check today. And in order to do that safety check, I'm gonna need your help. Since you're here, go ahead and type into the chat, what are some things you think that I might need to wear or to have with me today in order to make sure that I'm actually being safe while I'm working with some heat and some other stuff? What kind of science gear I might want to have on me? I'm going to look at my computer over here real quick, see how it's going. So I'm going to want to wear some safety glasses, a mask. Hi, Cougar Creek Elementary. Welcome. So, because we want to be safe today, we're going to be wearing safety goggles when I do my demonstration. That's going to help protect my eyes. And my hair's a little short, so I can't put it back, but we're going to keep it up. And then I'm also... Wow, multiple people from Cougar Creek, welcome. I'm also going to need some safety gloves today to make sure that I'm actually protecting my hands. Hi, grade 4 students from Sunnyside, welcome. Welcome on in. Super excited that you're here. So I'm going to need my safety gloves and my safety goggles today, and then something else I'm going to need, oh my glove is stuck, is some tongs, and you'll see why in a little bit. But it's going to be my basic safety gear that I'm going to need today. And today we're going to do a really cool demonstration that you could do at home in your kitchen using pressure. So I'm going to turn my camera down, and to get started with our experiment or our demonstration today, I'd love for all of you to just make some basic observations of what we're working with here and kind of, you know, get a lay of the land, set the scene. So I'm going to turn my camera down, and I want you to take a look. We have two parts of our demonstration here. We have this over here, and then we have this over here. So feel free to take some time and type into the chat, what do you see happening? What are some of the materials you might recognize or not recognize? And while you do that, I'm going to get my chat up over here so that I can see what our friends on Facebook are saying as well. So what are some things you notice I've got with me?
Materials you might recognize or not recognize.
All right. So this is sparkly water. It is not to drink for adults. But you can see we've got a heater over here, and when it glows red, that's telling us that it's actually getting hot. So this is a soda can. It's a sparkling water can. Over here, we've got a pie tin, and we've got ice in it. So what does ice tell us about this water that we have over here? I might need a lab coat. I don't have my lab coat here with me today, so we're gonna singe my arm hairs off. So Deb on Facebook says we have a can being heated with water on the stove, carbonated water, ice and sparkling water. Yeah, so we've got aluminum can sitting on top of my stove, so it's getting hot. We have plain water with some ice over here in a pie tin. And I'll give you a hint. Inside of this can, I have a little bit of water, just a little bit. So these are the two elements of our demonstration today. And if I put my hands behind this can, do you notice anything coming out of the can at all? Do you notice anything happening? The ice is going to be much colder than the stovetop. Yeah, we're already predicting some things. So what do you notice coming out of our can? Anything? I'm going to get this going nice and high. So, we've got our can, we've got our pie tin. Now that we see all of this steam coming out of the top, I'm going to do something with my can. So make sure to pay attention nice and close to what you see happening. Let me get it nice and going. A good rolling boil. All right, what I'm going to do is I'm going to take my can, I'm going to flip it and put it into this cold water. And nice, thank you for Sunnyside grade 4. You're noticing all of that steam. That's a good sign, that's what we want. And that's that water inside. And I'm going to flip it and I'm going to put it in here. So go ahead and make a prediction what you think might happen before I do it. I just want it to heat up a little bit more. Just a little bit. All right, let's see if we can get our demonstration to work today. Are you ready? We're gonna go quickly, so pay attention. We're ready in 3, 2, and 1. Whoa! All right, help me out and give me some explanations. What did you just see happen to our can? And while you do that, I'll get another one going. We know that's what we want. Ooh, you thought it was going to melt the ice? Good prediction. The can will warp. Good prediction. So what did you notice happening as we put our can upside down? What do you see? Looks a little different in my opinion, slightly different than it did before. So what happened to our aluminum can? Ooh, Gravity 101 on YouTube says it imploded. It collapsed. Yeah, it looks like it collapsed. It looked like it imploded. The water was sucked out of the can. These are great observations. Yeah, it looks like we basically crushed our can by flipping it over and putting it into our cold water. It looks like it got pinched. Yeah, not too much, but a little bit, you know, it got pinched a little bit. What, was the can empty to begin with? No, there was a little bit of water in the can about to here, so we had some water inside. So we see that the can was bent out of shape, it imploded, it crushed. It basically self-crushed a can. So we crushed this can using these two different things. But I want you to think in your head. if you've ever seen a can get crushed before, what do we typically do to a can to crush it? What is the action or the things needed to crush a can in our day-to-day lives? So you need to think about that and type a response in the chat. What do we typically do to a can, or what do we need to crush a can like this? So I'll give you a minute to kind of think about that and type it in. What do we do to crush a can? Nice. So we already have some folks kind of explaining what's going on with our science here. So typically when we crush a can, we might use our shoe against the sidewalk to crush it down. We might need force, which is a type of pressure that we're going to push in on the can to squeeze it closed, maybe with our hands if we could do that, or with our stomping on it with our foot to crush it really small. Or if you're wild, maybe you crush it on your head. I can't do that. So we need pressure. So we might need to use by stepping on it or using a hammer. Yeah, these are really great ideas from our chat here. So when we want to crush a can, we need pressure. We need a force that's going to smash it up nice and small. But when we did this demonstration, I wasn't using my hands, and I wasn't using my foot, and I wasn't using a hammer. So what do you think that invisible force might have been that was applying the pressure to this can to get it to crunch up the way that it did? And while you think about that, we'll do it again. That might help to get another observation in of what happens to our can. So think about the two pieces of our demonstration. And what might be that invisible force that crushes our can? Uh-oh. Am I frozen? Sunnyside, Luke, you're saying maybe we could use a vacuum? Let me refresh my computer. All right, folks, my computer on the other side has frozen up, so I'm just here on this one. But basically, we have some guesses. Maybe the heat and the ice are colliding. Maybe we're using a vacuum. So let's try it again. So we have this invisible force that's crushing our can. We have our can that's heating up on our stovetop. It's creating that steam because remember there's a little bit of water inside our can. And then when we move it over to our cold water on our pie tin, what do you predict is going to happen this time? Things in a vacuum implode. The cold sucks up all the air in the can. The heat made the can expand. Then the cold reversed it and made the can shrink. These are some really, really great guesses. Seeing if I can get our Facebook chat to load. Oh, nice. Okay. All right, let's do it again. Let's see if we can get the same result because science, you want to repeat it multiple times. Make sure it's valid. Make sure it's true. All right, ready? Let's do it again. See if we can get the same result, that implosion, in 3, 2, 1. Oh! All right, same result. And I think several of you have already helped us explain what's going on here. So let's break it down. And while we break it down, we will get another can actually going because third time is the charm. All right, so round 2, can shrank again. So we've got another crushed can thanks to our demonstration. So we've got some really good guesses from our chat here. Maybe heat made our can expand and then the cold reversed it, made it shrink. We have a question, is gravity doing something here? Well, gravity has something to do with it, yeah. And we'll get into a little bit in a minute. But gravity kind of helps us have our atmosphere and the pressure that we can create here on Earth, whether we're high up in the sky or down low on the ground. So let me just check our chat on Facebook. Cool. So a lot of good guesses, and you're all pretty much right on track. So what we're seeing here is a concept called implosion, which many of you put into the chat. And an implosion is kind of the opposite of an explosion. Rather than something blowing up and sending all of its energy outward, we have something collapsing in on itself as energy is sent inward. So implosion we can use to crush a can on its own. And we're using pressure. Just like I said earlier, we might use our hands to push down and cause pressure or force to crunch our can. But the pressure we're using here has to do with that steam that we're seeing. So inside of our can we had water. And I want you to think in your head, what happens when you take water and you put it on the top of a stove? Say you have a pot of water, you put it on the stove, and you heat it up over time. What happens to that water? What does it change into, and how do you know it's changing? So I'll give you a minute to type that in. Can you have, we have a question from someone on our Facebook chat. If we had no opening, what would happen? It would probably explode because there would be a buildup of pressure inside of our can and there would be no way for it to release. So good question. Let's see. When we boil water on our stove, we see that water, that liquid water, starts to heat up. It bubbles up, it creates those bubbles, it rolls, and then we see the creation of a gas. And when we see water boiling, it creates water vapor. We like to call it steam. So water vapor is liquid water that's been heated up and turned into a gas. If you were to cool water, it turns into ice. These are the 3 states of matter of water. Now when we heat up the liquid water inside of our can, it creates that liquid or that water vapor, that gas. So we can see that we have steam coming out of our can on our stovetop. If you could imagine what the inside of our can looked like. When we first started, you can imagine our can was a little bit filled with water and a lot filled with air. All of these air molecules were bouncing around in the top. But when we heat it up and that liquid water starts to turn into a gas, into water vapor, it actually fills up the top half of that can. And that water vapor starts to fill the can, and when it does that, it's actually pushing all of the air molecules out. You can imagine if you're in a room and it gets really crowded, sometimes you gotta, ask some people to leave the room. So you can imagine that the water vapor in our can, it's a little pushy. And as it fills the can, it pushes all of those air molecules out. So then our can is filled with water vapor, which is great because water vapor is great. We need steam, and it's filling our can. And we can see that there's an excess of that water vapor because of that steam. The steam we see rising out of the top of our can as it heats and boils on our stovetop. So we essentially have a can right now that's filled with liquid water and water vapor and almost no air. But when we turn our can upside down and we put it into our cold water in the pie tin, something happens to that water vapor inside. Does anyone know what happens on like a cold morning when you wake up and there might have been a lot of water in the air? Maybe it was foggy, maybe there was lots of clouds, and you look at the window. What do you sometimes see on the window in a cold morning? Little drops of it. So it's kind of the opposite. When we take water and we heat it, we get water vapor. But what happens when water vapor cools? Cougar Creek says condensation. Yeah, we see water vapor condensate, which means it starts to cool and condense back into liquid water. And it forms those little dewy drops of water on your window. So when we cool down water vapor, we get water. Maybe it's fog, maybe it's condensation. These are all really good words to explain it. So when we cool down our can that's filled with water and water vapor, we have a conundrum on our hands. When we flip our can over into our cold water, all of the water vapor that was in the top half of our can quickly cools and it condenses. That means it shrinks up back into water drops and joins the water. But remember how all of that water vapor was taking up all of this space and kicked out all of the air? Now there's no air inside of our can to take up this space. This creates an imbalance of pressure. There's a lot of air on the outside of our can, pushing inward, kind of forcing its way, but there's no way for it to get in because the bottom of our can is in the water. So this creates a lot of air pressure on the outside and almost no air pressure on the inside, which means the only way for the pressure to balance itself out, which is nature's most preferred state in balance, is for this can to implode and take up less space. So that way there isn't this massive imbalance with lots of air pressure on the outside and no air pressure on the inside. Because of our can being so flimsy, the can kind of loses in this situation. It's going to implode so that there's less space, but an equal amount of pressure than before. So basically, what we're seeing in our demonstration is that as our water boils, it takes up more space inside of this can as water vapor. And when we put that into our cold water, that water vapor cools, taking up less space, creating a huge imbalance in pressure between the outside atmosphere and the inside of our can. And nature does its own way of creating equilibrium, so it crushes our can so that there's equal pressure on both parts. Just to see if that actually works one more time, let's try it. One more time. This is my last can, so let's see if we can get it to crush one more time. Whoa. That was a really big one. Woo! It's fun stuff. So, once again, we see all of the pressure that was on the outside of this can, all of the air, pushed the can inward because there was almost no pressure on the inside. So to balance out this high pressure, low pressure situation, the can, which is super flimsy, crushes underneath the weight. You may also notice that this can sucks up all the water inside. So does anyone have a guess or an explanation? Why does that happen? Why does the can suck up all of the water inside and then we have to pour it out? Maybe there's too much water. All of the water and the air are forced out. Sophia says the air is gone. Yeah, when the air disappears, there's no air in here and there's no air that can get in, so we have water going inside. Keep making guesses and I'm going to show you one more demonstration that kind of shows us this concept. So we had all of that air sucked up into our can. We have a question, will this work the same way on a gas stove? It should. Just make sure that you're extra careful with your safety gear. So in our can, we saw that a bunch of the water actually sucked up into the can. And someone on our YouTube chat says maybe it was a vacuum, and you're right on. We're getting this vacuum effect that happens when we have this imbalance of pressure. Now we can recreate the same concept using a candle, water, and a glass. What I'm going to do is I'm going to put the glass over the top of our candle, and we're going to see what happens to the blue water on the plate. So this is just water with blue food coloring. And let's see what we notice. Interesting. So, if you noticed something, what did you notice happening? And why do you think that may have happened? Lucy on Facebook says it's like a vacuum and it sucks up the water. We've got someone else saying the fire will burn the oxygen out and cause a vacuum, sucking the water into the jar. Let's see if there's any other observations. The water rised or rose? Yeah. So if you looked closely, you may have seen that the water in our glass jar rose. It actually sucked up into our jar. And this has to do with the same concept of pressure. It's a little bit different because we're not, boiling a can and putting it in cold water, but we're still seeing a similar concept. As the candle heats up the air inside of our jar, it increases the pressure inside, but once the candle goes out, all of that air quickly shrinks up, taking up less space than it had been before. That causes an imbalance of pressure, where there's a lot more pressure outside and not very much pressure inside, which pushes the water into the jar to kind of balance that pressure back out. Now there's an equal amount of pressure inside this jar as there is outside this jar by creating this little vacuum seal. So nature kind of has its own way of balancing out pressures in objects like this. And if I have to pick this up, it has a little bit of a resistance, but once I break that seal, whoop, it all comes out. So pressure can be really fascinating, but it can also have really cool implications for our day-to-day life. For example, how many of you have ever been riding in a car or maybe in an airplane, and as you go up a hill or high into the sky, felt your ears feeling kind of full, like a lot of pressure was suddenly put on them? Have any of you ever felt that before? Oh, where did the air go? Well, the air was still inside of our jar. You can imagine air as invisible little particles that are bouncing around. So as the candle sat in the jar, it made the air get really excited, and it actually pushed some bubbles out because the air was expanding. Kind of like if you blow up a balloon, you're expanding that balloon by adding air. When we heat up air, that air gets more energetic and it pushes, it causes pressure. So there was not as much air in here as there was originally, but the air was still in there when the candle went out. The air cooled and took up less space, and then there was that imbalance of pressure. So there was still air in the can, or in the glass, and there was still air outside. It just kind of moved and acted differently. So it didn't necessarily get burnt up, but it kind of got pushed out. Oh, we had a question on YouTube. Why did the candle stay lit for so long? That's a really good question. And if you know, what does a fire need to actually live? And we can do this again if you want to watch again. But a fire needs a few things to live. It needs fuel, like a light, and it needs oxygen. So when I put this candle, let's see, it might have gotten wet, so we'll see if it actually wants to light. It's going. So when I put the candle underneath the jar, this jar has some oxygen in it that allows the candle to burn off of like fuel. But once all of that oxygen gets cycled through, then there is no more left and that candle is basically smothered. So it burns for a little bit. It's kind of using that oxygen inside like fuel. But once it runs out, and because this is a big jar, it probably burns for a lot longer than you would expect. Now all of the oxygen is gone, and that air inside is cooling down, taking up less space, causing this imbalance of pressure, so the water is being sucked up inside to reduce or to increase the pressure in our jar. It's complicated because a lot of it's invisible, so it's a little bit more challenging to picture. But like I said, it's kind of a cool thing. You can actually do this at home if you have a little candle, and you can do this with some water, with a jar, and you can try different shaped jars or maybe different amounts of water, different types of candles to see how that affects your actual results of how it goes up or goes down. And then we'll just kind of do, whoop, uh-oh. I'm making a mess today, everyone. That's okay though. So overall, pressure is really important. It can kind of help us know how things are going to change when we are changing our altitude. If you go up high into the sky in a car, your altitude is increasing. This all has to do with air pressure. As you go high into the sky, there is less dense air. So the pressure around you has decreased, but that means that the pressure inside of your ear, in your eardrum, has stayed the same. And in a response, the air inside your ears expands, and it feels like it's pushing on your eardrums. Sometimes you have to pop your ears. And that's all dealing with the same concept, that you have high pressure inside your ears and lower pressure outside of your ears. So they have to find a way to balance. And typically whatever the weaker thing is, if it's aluminum can or if it's your ear, that's going to be the thing that shifts a little bit more than the other thing. You can also think about if you were to ever go to space. Space is a vacuum, meaning there's almost no pressure out in space. So when engineers and scientists are building a rocket ship to go somewhere where there's no pressure at all, they have to kind of figure out how might things react under no pressure versus regular pressure. Or if you take a rocket ship that needs to be pressurized into space where there's no pressure, how do you balance those two things out so that you don't have a rocket ship that's exploding or something that's imploding? Although the ship would explode. Something that might implode would be a submarine. If you take a submarine and you are swimming along in the sea, the deeper you go underneath the ocean surface towards the bottom of the ocean floor, the more pressure that submarine is going to face as it travels down. That means that the submarine you have built better be pretty strong. Otherwise, the high pressure of the outside of the submarine might crush it, which wouldn't be great, especially if there's people on board that submarine. So knowing how pressure works and doing some tests with pressure like this can just get us more familiar with how it works in our day-to-day lives and how it has bigger uses when it comes to building large machines like submarines or rocket ships. Now, if you have any questions, feel free to type them into the chat. I think we have one over on Facebook, so I'll read that, but feel free to type your questions in the YouTube chat or the Facebook chat, and I'll answer as many as I can. It is 11 o'clock, and I know that some of you usually have something scheduled afterwards, so thank you for joining if you have to go. We won't be doing a show next week, but keep your eyes peeled for our upcoming events to see if you want to join us for our telescope viewings, which happen every Saturday. We also have a talk this Friday about sci-fi and actual space travel and how sci-fi has kind of influenced space travel from one of our staff members, Ben Buress. So you can check that out. And yeah, Life Science will return shortly, and we'll let you know when we'll be back, what we'll be doing, and we'll try to continue bringing you some free virtual programming into your homes. If you'd like to donate to help support all of our virtual programs, such as this one, feel free to click that donate button or head to ChabotSpace.org and you can make a donation there. Thank you in advance for anything you are able to give. And if you or if you're not able to support in that way, feel free to just attend and support by being here. Just showing up is really important these days. So thank you all so much for being here. All right, question on Facebook. So the burning up of the candle uses the oxygen, but at the same time is producing carbon dioxide. So why doesn't this balance out the pressure? Ooh, that's a good question. I'm not positive, but I'm assuming that maybe carbon dioxide takes up less space than oxygen. When it burns, it might take up less physical space the way it moves throughout the container, so there's still an imbalance of pressure. But I'm not sure. That's actually a really good question, because you're burning gas and creating gas, so why isn't that staying equal? I don't know. That's a good one. But that's my guess, is that carbon dioxide as a gas takes up less space. And Cougar Creek students, thank you so much for showing up. We love having you. And yeah, y'all have been great. Lots of good questions, lots of good ideas and observations. A really good bunch of scientists up there. Any other questions that we have from our friends out there on YouTube or Facebook? I'm really intrigued by the carbon dioxide one. I'm not sure. And if you try any of these experiments at home, feel free to tag us, let us know that you're doing them. Most of these you can do at home, but they just take a little bit of help, a little bit of adult help, and just a little bit of safety gear. If you don't have goggles, you can wear sunglasses or regular glasses. So there's ways to do science at home safely that doesn't require a full lab coat. Thank you. Love our Facebook top fans. The difference is that the carbon dioxide also was heated. So it's still cooling and it's still contracting and it's still creating that difference in pressure. That's totally right. It's not a matter of gas, it's a matter of temperature and its size and pressure. Thank you. I love it when I get help from the audience. All right, everybody. Thank you so much for joining us. Hopefully you have a wonderful holiday break, and make sure you're staying safe, make sure you're wearing a mask, make sure you are telling everybody that you love them and that you're doing science, you're staying curious, and that if you're looking for resources, come visit us at Chabot. We're always happy to provide more. So thank you all so much. Have a wonderful rest of your Wednesday, and we'll see you around. Stay safe, stay curious. See you next time.